So in a typical block diagram of a communication system, I would have the following blocks. I would have a source of information, and then I would have a possible transducer, to convert it into a form which is to be transmitted into. Then I have a modulator, then I would have a multiplexer, I'm going to have a channel here, I'm going to have a demultiplexer, I'm going to have a demodulator, and possibly a transducer at the receiver end, and then finally the destination of information. This is how I would finally conclude the typical blocks of electronic communication system, and may it be the analog or digital. We have various other blocks adding up into this, but more or less this is the kind of blocks which we would see in any kind of communication system, no matter whether it is a wired communication system or a wireless communication system. Now let me continue from the part of modulations, whatever that we have discussed in the previous session. As I said, I have an information source, I have a transmitter, then it has been channeled into the channel. I have a channel here, and then I have a receiver at the receiving end, and I have finally the destination. As we were discussing the importance of modulation, why we require modulation, which is a very important part of all your communication system. The first part, which we've already discussed the other class, was about height of the transmitting antenna. The second parameter is going to be the noise immunity. The third one is going to be multiplexing. In fact, these are the three major advantages of why I need to have modulation of my information signal in the communication channel. We've already discussed the first part of the aspect, like the height of the transmitting antenna, and the other class I've already given you the illustrations of mathematical consequences of having lesser antenna height, and for that why do I need to increase the frequency of my transmitted signal with the help of the carrier. Now the second point which I'm going to concentrate now is the noise immunity. As I discussed in the very first class, that noise is a relative parameter, or it's a relative concept. In the channel, this particular channel which I have here is being shared by many users. This is not a dedicated channel. Of course, I do have dedicated channel, but I'm now talking about a wireless channel which is a shared channel between many number of users. Now in that case, my point of noise being a relative parameter plays a very important role. This statement has a very importance in the shared channel concept. Now, as I said, the channel is being shared by various users, I have a kind of communication between A and B, and I have a communication between C and D. Now, for the signal received by D, I have the signal transmitted by A plus the signal which is added up from C, and here in this case, since for B the signal from C is unwanted, I am calling C as a noisy signal for B. But in a similar way, for D the signal coming from A is also called noisy, because for D the signal coming from C itself is the desired signal. So this point makes it very clear that noise is a relative term subjected to which user's communication you are talking about. The communication between which two users is going to influence the term called as noise. Now, another important aspect of noise is frequency selective. What do I mean by this? This characteristic feature of noise is helping the analysis of communication system to a great extent. Now, when I say noise is frequency selective, let me assume that a particular signal is transmitted with a bandwidth of about 10 to 30 kilohertz. With a bandwidth of 20 kilohertz, the signal being spread between 10 to 30 kilohertz has been transmitted from the transmitter. And now let me assume that the noise is having a dominant peak at 20 kilohertz. So in this case, majority amount of your message signal is being influenced by this noise peak at 20 kilohertz, because it is disturbing most of the signal in that bandwidth. Now, if I say I am modulating my signal to a central carrier frequency of say 100 kilohertz with again a bandwidth of 20 kilohertz from 90 to 110 kilohertz. Now in this case, though the signal strength is low, even though the signal strength falls down in this range, it is not being affected by noise, because the noise peak was only existing at 20 kilohertz. Now the noise which was affecting your signal at 20 kilohertz is not coming to your signal at 100 kilohertz. Now this is the very important aspect, second very important aspect of your modulation, wherein by modulating a low frequency signal to a higher frequency band, you can avoid the effect of noise. Now I am saying I can avoid the effect of noise, but I cannot remove the noise, because there might be some other sources of noise in the vicinity of that bandwidth as well. So more or less, by selecting a frequency band which is noise free, I can avoid noise being interrupting my signal. So this is the second use of so-called modulation. Now the third use, as I was talking about, is multiplexing. Now consider a situation wherein there are two users, or let me consider this case in a more Now consider I have on the transmitting end A1, A2, A3 and A4 as the users, and let us assume that they are communicating to users B1, B2, B3 and B4 on the other end. Now let me say that these four users are trying to have a communication sitting here in Hyderabad, and let us say these four users are somewhere in Delhi. Makes more sense. Now the users, if they are if they wanted to have a communication from peer to peer, that is, if I wanted to have a line from A1 to B1 and line to A2 to B2, A3 to B3 and A4 to B4, our Indian economy is not going to bear this. The telecom sector is not going to bear this because it's going to be pretty costly. You already know the distance between Hyderabad and Delhi. It's very long, and laying each individual line is not possible practically. So what do is they try to map a single line between Hyderabad and Delhi, and they all map you onto that single line. That is, say now I have a line from Hyderabad to Delhi, let me assume, and in that A is mapped to this, B is mapped to this, C is mapped to this, and also D is mapped to this. Similarly, it has been demultiplexed at the other end. This way, for almost a lot of your distance between Hyderabad and Delhi, a single line of communication is going from here to here. That is, you do not need to have individual pairs. Now, the basic question here is, the basic concept of doubt here which you might come across is, are they not going to interfere? If I have 4 people and 4 people's signal are also put on a single line, and as I said, like your voice frequency is common for everybody who speaks. So if 4 people are having a conversation, there are quite chances that the frequencies of those particular voice signals are going to be very close on spectrum. So now the practical problem is, I got to have a single line. At the same time, I do not want the interference of signals from one user to the other user. So for that, I typically use this modulation, wherein I try to map the baseband signals of individual users into a broader spectrum. Say for example, if I am having this thing at 3.3 kilohertz, 3.4 kilohertz, 3.5 kilohertz, and say 3.6 kilohertz. Now in this case, all the frequencies which are generated by 4 users are exactly 0.1 kilohertz apart. They are very close. Now if I am using a carrier frequency of say 10 megahertz, now this would be 10 megahertz plus or minus 3.3 kilohertz, 10 plus or minus 3.4 kilohertz, 10 megahertz plus or minus 3.5 kilohertz, and 10 megahertz plus or minus 3.6 kilohertz. This way, I am creating a separation between these individual channels by an amount of 10 megahertz at centered. So 10 megahertz is a very big quantity. When you compare with 0.1 kilohertz, 10 megahertz is going to be a very big quantity. So this way, now I am trying to take a single carrier at 10 kilohertz, and in the same channel, same carrier, using the same carrier, I am modulating all the 4 different types of message signals. Thereby, I can send all these 4 in one single message across one channel. Now this process of sending more than one signal through the same communication channel is called as multiplexing. So this concept is called as multiplexing. So now what is multiplexing doing for you, apart from avoiding the interference, avoiding the inter-user interference? What else is it giving you? If I ask me this question, I get an answer that it is conserving the bandwidth. It is conserving the bandwidth in the sense that if I would have had to give a leased line, individual line like this, say for example, this has to be given at 10 kilohertz, this has to be given at 20 kilohertz, this has to be given at 30 kilohertz, this has to be given at 40 kilohertz. If I give individual frequencies, individual high carrier frequencies to these, then this is wasting my bandwidth. So multiplexing has brought 4 different signals onto a single channel, and it is doing the job of conserving your bandwidth and also doing the job of avoiding your interference from multiple users. So that's the story all about modulation, why we require modulation. And now a block called as modulator in your transmitter does all this job. And as we've already described in the earlier class of typical introduction to communication system, we've also mentioned a block there called as multiplexer. Now this is what a multiplexer do. After the modulation has been done, it tries to put multiple channels, multiple frequencies onto a single channel, and then it transmits. So here we complete a very brief discussion regarding your transmitter. Now in the block diagram I have given an antenna there, because basically all these parameters are happening in your electrical quantities, all these modulations and multiplexings and all becoming your they are done in electrical quantities. But now they are all at the higher frequency side. After modulation they have gone to radio frequencies. But now when you wanted to transmit the same signal into a wireless medium, a wireless channel, just your process, I mean, as we said, like it is not going to have a kind of physical medium. You are not going to have a wire in a wireless medium. It is just going to be free of wires. So now your signal is to be transmitted from one end to the other end, where the distance of transmission is very high. Now this is what I call it as free space propagation. Now when I come to the channel again, here after completing a brief discussion of this, I have the concept of a channel. As I said, this channel can be of two types. It can be a wired channel and can be a wireless channel. Wired channel could be typically like your a coaxial cable or an optical fiber cable. And here this is a free space propagation. Now when I come to the radio waves, especially your frequency range from 3 to 30 kilohertz, 30 to 300 kilohertz, 300 to 3000 kilohertz, this is typically called your high frequency range. This is called as your VHF range, and this is called as your UHF range. So typically we are talking about wireless communication in a free space media, mainly about these three frequency bands, which are broadly called as radio frequencies. Now depending upon the kind of frequency that we use, now let me just deviate and let me complete few typical points about this wired communication, because in a typical communication system we will be more talking about free space propagation, but let me also have a little bit talk about coaxial cable and optical fiber. So here coaxial cable and optical fiber, you are going to have a dedicated line from transmitter to receiver. So obviously you are not going to have much of the distortion or much of the attenuation which you typically find in a free space propagation. And in the coaxial cable, you typically have the signal being converted into a electric form. The signal is traveling in the form of an electric signal, and in the optical fiber the signal is transmitted in the form of a optical wave or light. It travels in the form of a light. So depending upon what is the nature of the signal, the medium has to be shaped. I mean, the type of medium through which it is going, the medium characteristics will depend upon what kind of signal it is. If it is optical signal, I have an optical fiber system which has got typical arrangement for that propagation of a signal. Similarly, for a coaxial cable, I have twisted pairs and coaxial cables also, which vary in their construction in the form of the type of signal which they are carrying. Okay. Now, keeping aside this wide channel where I have more reliability, less attenuation, but this cannot be operated over longer distances. So, for obviously longer distances, when I am modulating a signal, I need free space propagation. Now, the free space propagation basically takes place in radio frequency bands. Now, when I am talking about free space propagation, as I was talking about the transmitter here with an antenna, this antenna parameters again depend upon what is the kind of frequency band that you are trying to use for your radio wave propagation. So, if it is high frequency, you are going to have different parameters. If it is very high frequency, you are going to have a different parameters, and if it is ultra high frequency also, you are going to have a different parameters for the transmission of that signal through this antenna. So, the typical parameters of the antenna, like antenna gain, directivity, power, effective aperture, and half power beam width between full nulls. So, like this you have various parameters of the antenna which are to be taken care depending upon what kind of frequency band you are choosing to transmit your signal into the free space propagation. So, again you have a lot of other parameters like impedance matching of your antenna terminal to the free space impedance, characteristic impedance, and all those parameters are there which link up to your RF parameters, RF modeling of this antenna. All those things which we would come at a later stage. Probably this is a different wing of communications which purely talk about the RF characteristics of your transmitter channel and the receiver. Now, keeping aside this part, now as I was talking about your channel as medium of communication, now let me be more precise and refine this term of channel by including more practical constraints of a communication system. Now, when I say a channel as a medium, it is a very crude definition of channel. The more refined form of definition for channel would be it tries to change the characteristics of a signal. Now, if I am going to call my input signal as x of t, my channel to be having a function, a transfer function called as h of t, and my output going to have a function y of t, then I would call y of t as x of t convolved with the transfer function of the channel. This is more meaningful definition of what is so called a channel. So, now I would refine the definition of channel as not merely mode of medium of communication, but I would call now the channel as a block, channel as a transfer function which is changing the characteristic of your input signal. So, my input signal is convolved. So, what are the things that are changing the characteristic of a signal in a channel? As we have seen that in a channel, any radio wave will try to attenuate in its strength as it is traveling from one point to the other point. So, as the radio wave travels, it loses its energy and hence the signal gets attenuated. That is one point of the channel introduces attenuation, decrease in strength. That is one thing. Second point which you are going to have in your channel is additive noise. You are going to have an additive noise. And the third most important area of research for the people who are more interested into the channel characteristics is the distortion. So there are two things. These three different terms are causing the input signal characteristic to change in two things. One is the attenuation and noise, they tend to decrease the signal strength, but whereas the distortion is changing the shape of the signal. So if I have typically a signal like this, only the attenuation and additive noise are going to decrease its strength. They are going to disturb its strength. It is going to decrease in amplitude. But now the distortion is not only apart from your attenuation and additive noise, which are trying to decrease the strength of the signal, the distortion is changing its shape. So this is how basically a signal is getting affected by these three parameters. One is your attenuation, the second one is the additive noise, and the third one is distortion, which is more and more typical for any kind of communication engineers, and the lot of work, lot of your computational complexity goes into receiving the receiver, in designing the receivers where you have more amount of distortion. So basically this is the mode of channel.